Welcome to Lecture 18 of CS 182. In today's lecture, we're going to continue our discussion of generative models from Monday and talk about latent variable models. Specifically, we'll discuss variational autoencoders and another kind of latent variable model called a normalizing flow. Okay, so let's just briefly recap from last time. Latent variable models, as discussed in this course, are models for representing some complex probability distribution P of x by using two simpler probability distributions. A simpler probability distribution over a latent variable, which we're going to denote with z, and that might be something like a unimodal Gaussian distribution, and a conditional distribution, which is conditionally Gaussian given z. So this might mean that P of x given z is Gaussian with mean given by some complex neural network function of z and variance given by some complex neural network function of z. So the idea is that we've replaced the need to represent some really complex distribution P of x with the need to represent two much simpler distributions, P of z, which is just fixed, like a Gaussian, for example, and P of x given z, which is a simple distribution, like a Gaussian, but where the mean and variance are very complex deterministic functions of z. So instead of having to represent a really complicated distribution P of x, now we have two simple distributions and a complex deterministic function. And the reason this is desirable, of course, is that we know how to train deterministic functions. We do that using neural networks. So that means that P of x is given by the integral over all possible values of z of P of x given z times P of z. That is, we need to integrate out z to get P of x. Now, of course, in reality, when we work with latent variable models, we're going to try really hard to avoid ever having to evaluate this integral. If we want to sample z, if we want to sample x, that's actually very easy. All we do is we sample z first, and then we sample from x given z. The place where the integral becomes problematic is when we want to train this model, because we would train with maximum likelihood, and that requires somehow estimating P of x. But the integral consists of the product of two easy distributions, P of z, which we refer to as the prior, and P of x given z, which is our learned model. Okay, so how do we estimate the log likelihood for training? Well, instead of evaluating this integral, what we're going to try to use is the expected log likelihood. And again, I will present the expected log likelihood somewhat heuristically here, but we'll actually see later in today's lecture why the expected log likelihood is actually a principled way to train these kinds of models. So the intuition behind the expected log likelihood is that instead of evaluating that whole integral, what we're going to do is we're going to take our data, which consists of x's, and we'll basically make up z's that we think are likely to go with those x's. So what we would really like is a data set that consists of x's and z's, though of course we don't know what the z's are, so we'll just guess what the z's might be, pretend that our guess is correct, and then maximize the joint probability of x and z. Because when we have the joint probability, then we don't need to evaluate that whole integral. So the way that we're going to guess the z is by taking an expected value under P of z given xi for every data point xi in our data set. And then we'll maximize the joint log probability of xi and the z that we guessed. Now that's the intuition. Of course, in reality, P of z given xi is a distribution, meaning that we don't know exactly which individual z goes with which xi, but we can guess the probability of different z's. So what we have to do is we have to actually average over all those possibilities, and that's what an expected value does. And of course, in reality, the way we estimate this expected value is by sampling from P of z given xi, and then maximizing the corresponding log probability of xi and z. So the intuition is that we're going to guess the most likely z given xi and pretend that it's the right one. But there are many possible values of z, so we use the distribution P of z given xi, or some estimate of that distribution. So the big challenge with this scheme is how do we calculate P of z given xi? So we've essentially transformed this problem of evaluating that intractable integral into the problem of somehow estimating and then sampling from P of z given xi. And this is called probabilistic inference. The reason that it's called inference is because we are inferring which z goes with a particular xi, which latent variable goes with a particular image, let's say. So our generative model takes us from z to x. The inference process needs to take us from x back to z. And of course, the distribution over z's that corresponds to a given image x might be fairly complex. So you might imagine that the z's represent some underlying factors of variation in the image, like, is there a dog? Does it have a nose? Does it have 2 ears? Does it have 2 eyes? And we have a lot of uncertainty about all these things because we might not see everything in the image. So we might have some very complex distribution over z given a single x. So inference in general is a very difficult problem. But what we'll talk about today is how we can perform approximate inference, how we can approximate p of z given xi, and from that we'll actually derive a tractable way to train these complex latent variable models with neural networks. Okay, so the basic idea behind what we're going to do is called the variational approximation. And in the first part of today's lecture, I'll go over variational inference in general, not specific to deep learning, and then I will, in part 2, discuss amortized variational inference, which brings in neural nets to make it more practical. Okay, so this part is going to be somewhat mathematically involved, so bear with me. If some part of it is unclear, do make sure to come to class and come to section to cover the details. Okay, so here is the basic idea. Instead of actually calculating the real distribution p of z given xi, we're going to approximate it with some much simpler distribution that's much easier to deal with. For example, we might just say that p of z given xi for a particular image xi is some Gaussian with some mean, mu I and sigma I. And it's going to be a different mean and a different variance for every image. So for every data point in our data set, we have a different approximate distribution qiz, and we're going to try to get that approximate distribution to be pretty close to the real posterior p of z given xi. Now, of course, the real p of z given xi is not just a Gaussian. It might be some really complicated thing. So this is an approximation, and perhaps a fairly crude one. The remarkable fact is that for any choice of qiz, we can construct a lower bound on log p of xi. So the quantity that will work out is not equal to log p of xi, but it is less than or equal to it, which means that if we're trying to maximize log p of xi, we can maximize this lower bound quantity instead. So if you have a particular function that you want to maximize, and you have another function that's always less than or equal to that, if you push the lower function up, eventually it'll push up your objective value. So that's why it's really interesting that we can bound log p of xi. So here's how we can do it. Let's start with the expression for log p of xi that uses that intractable integral from before. So we know that log p of xi is the log of the integral over all values of z of p of xi given z times p of z. And now we can multiply the quantity inside the logarithm by 1. And qiz over qiz is equal to 1. We didn't change anything, we just inserted this little fraction here. We know it's equal to 1, so we can always put that in. And now we'll slightly rearrange the terms. Because you see, we have an integral of some quantity multiplied by qiz, which means we can also write it as an expected value under qiz. We didn't change anything around, we just rearranged the terms a little bit. So inside the expectation are all the terms except for the qiz that used to be in the numerator. So we're left with pxi given z times p of z, and then the qiz that was in the denominator. Okay, so we've just rewritten this integral as an expectation. And now we're going to apply a mathematical identity that is at the core of the variational approximation, which is Jenkin's inequality. Jenkin's inequality allows us to bound any concave function below, any concave function of an expectation below by the expectation of that concave function. If that doesn't make sense to you, don't worry about it. The only really important thing that you need to know about Jenkin's inequality is that if you have the logarithm of an expected value, that quantity is always greater than or equal to the expected value of a logarithm. So if you push the logarithm inside the expected value, that lower bounds the logarithm of the expected value. Jensen's inequality in general can be applied to any concave function of which the logarithm happens to be 1. Or if it's a convex function, then the inequality goes the other way. So if we apply Jensen's inequality to the last line of that derivation on the left, then that means that the logarithm of the expected value under Qiz is greater than or equal to the expected value under Qiz of the logarithm of that fraction. Okay, so we just push the logarithm inside the expectation. And again, this quantity is not equal to log p of xi, but it is less than or equal to, which means that if we want to maximize log p of xi, if we instead maximize the last line here, it's always less than or equal to, so as we push it up, eventually it'll push up log p of xi. And that expression on the last line is going to be much more tractable to estimate in practice and will allow us to construct a viable learning algorithm. So now we'll do a little bit of algebra to turn this last line into something that we can actually optimize with gradient descent. So first we're going to apply the very useful identity that says that the logarithm of a product is equal to a sum of logarithms. So since we have a logarithm of p of xi given z times p of z divided by qi of z, that is equal to the logarithm of p xi given z plus the logarithm of p of z minus the logarithm of qi of z. And I've specifically broken out the expectation, so there's one expectation around the positive terms and another expectation around the negative terms. I can always do that by linearity of expectation. And that's because that last term actually has a very special meaning in information theory. See, the last term here, the expectation under qi of z of log qi of z, is the negative entropy of qi. Entropy is a very special quantity in information theory that I'll talk about shortly. But the conclusion of all this discussion is that maximizing this quantity that I have at the end is going to push up on a lower bound to log p of xi, which means that it will eventually maximize log p of xi as well. There's a little detail here, which is that we do need to know how tight that bound is, and we'll talk about that a little bit later. But first, let's have a few brief asides about information theory. First, let's talk about differential entropy. So I mentioned before that this quantity, let me just rewind for a second, this quantity right here in the bottom right, this is just the negative entropy of qi. So there's a negative sign in front of it, which means when we have the negative entropy, that's just the entropy. What is entropy? Well, if you look up entropy in Wikipedia, you'll see this expression. The entropy of some distribution p is just the negative expected value under p of x of log p of x. Okay, that maybe seems a little cryptic. Here is the entropy for a Bernoulli random variable written as a function of its parameter, right? So the Bernoulli random variable is the probability of a coin coming up heads, where the parameter is how much the coin is weighted towards heads. And if the coin never comes up heads, meaning the probability is 0, or the coin always comes up heads, meaning the probability is 1, then the entropy is 0. So if the event is deterministic, there is 0 entropy. If the event is perfectly stochastic, which means the coin has 0.5 probability of coming up heads, then the entropy is maximized. So intuitively, entropy represents how random a distribution is. So if all outcomes are equally likely, then you have the highest entropy, whereas if one outcome is guaranteed, then you have the lowest entropy. So one intuition for entropy is how random is the random variable. Another intuition is entropy quantifies how large is the log probability of a distribution in expectation under itself. So, for example, if you have two distributions like this, these are now continuous value distributions. We could ask, well, which one has the higher entropy, the top one or the bottom one? Take a moment to think about this question. Make a guess. Does the top have higher entropy or does the bottom have higher entropy? Well, since entropy quantifies how random a random variable is, the top one has higher entropy because there are more values that are possible, which means the probability of each of those values must be lower, because distributions always integrate to 1. The lower one has lower entropy. In fact, in the limit, as that peak gets very, very tight, entropy will go down to 0. And if there's only one event that's possible, that is minimum entropy. So then we could ask, for the expression that we saw at the end on the previous slide, what would we expect this expression to do? Right? We're maximizing entropy over Qi. We're going to make this quantity big. And then we're also maximizing the expected value of those log probabilities. Well, the first term is going to encourage finding a value, putting a lot of probability mass on a value of z for which log p of xi given z plus log p of z is large. Pxi given z times p of z is just p of xi comma z, so we could plot that where z is on the x-axis and the probability is on the y-axis. If we just had the first term, we would basically just have a distribution Qi that puts a lot of probability mass on the largest point. But because we're also trying to maximize the entropy of Qi, we're going to try to make it as broad as possible. So what that means is that we'll capture the point with the largest probability under P, but we'll also make the resulting distribution Q as broad as we can, so that it covers as much probability mass as possible and has the highest entropy. Another concept in information theory that we should discuss is KL divergence. KL divergence, again, if you look it up on Wikipedia or in a textbook, you'll get a somewhat cryptic equation. The KL divergence between two distributions, Q and P, is given by the expected value under the first distribution of the log of the ratio of the two distributions. Or another way to write it is, if you use that property that the logarithm of a ratio is just a difference of logarithms, it's the expected value under Q of log Q minus the expected value under Q of log P. Which it can also be written as the negative expected value under Q of log P minus the entropy of Q. KL divergence can be thought of as a measure of how different two distributions are. Because if Q and P are exactly the same, then their KL divergence is actually 0. And it's easy to check that, because if it's the expectation under Q of log Q minus the expectation under Q of log P, if log Q and log P are the same, then those two will cancel and you get 0. As Q and P become more different, then their KL divergence increases. And the KL divergence is guaranteed to always be positive. Another intuition for it is, how small is the expected log probability of one distribution under another minus entropy? And that minus entropy part is important. Why? Well, because if you didn't have that, then you would just find, then the Q that minimizes that quantity would just find the peak of P. But because you're also maximizing entropy, you want to capture as much of P as possible. And of course, the lowest KL divergence would be if the two distributions match perfectly. So the expression that we derived before by using Jenkins Inequality is actually a KL divergence. We call this the evidence lower bound, sometimes denoted with L. And it's a function of two distributions, P, which is the distribution we're learning, and Qi, which is our approximation to the posterior. So what makes Qi of z good? Good meaning, well, what is good? That's a very important question. A good Qi of z is one that makes this bound as tight as possible. That basically makes the right-hand side of this expression as close as possible to the left-hand side. The right-hand side is always less than or equal to, but if we choose Qi of z well, it'll be very close to log p of xi. The intuition for what makes a good Qi of z is that Qi of z should accurately approximate p of z given xi. And I will show you why this is true. So in what sense should Qi of z approximate p of z given xi? Well, their KL divergence should be low. And we can prove this. Here's how we prove it. First, let's use the definition of KL divergence from the previous slide. So the KL divergence between Qi of xi and p of z given xi is just the expected value under Qi of z of the logarithm of Qi of z divided by p of z given xi. Now, by definition of conditional probability, pz given xi is pxi comma z divided by pxi. So if we substitute that in, then our KL divergence is the expected value under Qi of z of the logarithm of Qi of z times p of xi divided by p of xi comma z. And again, using the property that the logarithm of a product is the sum of logarithms, we can write this out in a somewhat complicated way as three expectation terms. The negative expectation under qi of z of log p of xi given z plus log p of z. Then the expected value under qi of z of log qi of z, which you'll recognize as the entropy, and then the expected value under qi of z of log pxi. And the reason that I split it up into three terms like this is that the third term is just log p of xi, because the quantity inside the expectation terms doesn't depend on z at all. The second term is the entropy of qi of z, and the first term is just the negative of what we saw in our evidence lower bound. So rearranging the terms a little bit, we can substitute in the entropy for the second term, and we can get rid of the expectation for the third term because the thing inside the expectation does not depend on z. And we can recognize that the first two terms together is just the negative of the evidence lower bound. And now we have a really interesting property. The KL divergence between qi of z and the posterior. I apologize, there's a little typo. That should be dkl qi of z, p of z given xi, not qi of xi. That's a small typo. This KL divergence is equal to the negative evidence lower bound plus log p of xi, which means that log p of xi is equal to the KL divergence plus the evidence lower bound. All right, so if I just add li to both sides, I get this equation. The KL divergence is always positive. So this is another way to derive the fact that li lower bounds log p of xi. But this derivation is a little bit more informative because it tells us how much error is incurred by using that bound. Basically, the smaller the KL divergence between qi of z and p of z given xi, the better li approximates log p of xi. And this is very, very important. It means that maximizing that evidence lower bound L will push up on pxi, and the smaller the KL divergence between qi of z and p of z given xi is, the closer L is to our objective, which means the more effectively it'll maximize p of xi. So if the KL divergence is big, then you can maximize your L all you want, but you won't move your objective. But if the KL divergence is small, then the only way to maximize the lower bound is to actually push up on log p of xi. So that means that if we get a choice in which qi of z to use, we want to pick the one that minimizes KL divergence to p of z given xi, which means we want qi of z to be close to p of z given xi. Okay. So here's what we've got. We've got our lower bound. We know that the smaller the KL divergence, the tighter the lower bound is. And the lower bound is always a valid bound. We know that the KL divergence between qi of z and p of z given xi can be expressed as the lower bound plus log p of xi. So that means that maximizing the lower bound, li of p comma qi, with respect to qi, minimizes KL divergence. Right? So if we want to know how to train our model, we can train our model by maximizing the evidence lower bound with respect to the model P. And if we want to get the best QI, we also maximize the same evidence lower bound with respect to QI. Because the only terms in the KL divergence between QIZ and P of Z given Xi that depend on QI are all the terms that are present in the evidence lower bound. So that's great. This is telling us that if we just maximize the same exact objective, the Li of P comma Qi, with respect to both P and Qi, then we will maximize our real objective value, log P of Xi. Because maximizing Li P comma Qi with respect to Qi will make the bound tighter, and maximizing with respect to P will push up on the bound and thereby maximize log P of Xi. And this can give us a tractable way of training latent variable models. Okay, how do we use this? Well, our goal is to approximately maximize log p theta of xi, but of course we can't do this exactly, so what we'll instead do is we'll maximize the evidence lower bound Li. So here's how it'll work. For every xi in our data set, or in our mini-bench, so here xi's might be integers, for example, we're going to calculate the gradient of the evidence lower bound with respect to the parameters of our model, with respect to theta. So the way we do that is we first sample a z from qi of z because we have an expected value. And then we approximate our gradient, which is the gradient of the expected value, as the gradient for our model for that one sample. Now notice that P of z doesn't have any parameters. P of z is just like a zero mean unit variance Gaussian. So the only term that depends on theta is P theta xi given z. And that has to be evaluated in expectation under Qi of z. So we sample z from Qi and then compute the gradient. That's a single sample estimate of that gradient. We could also use multiple samples if you like. And then you take one gradient ascent step on theta. And then you also have to update your Qi to also maximize Li, P, Qi. And there are a variety of ways to do this. We'll talk about how to do that soon. But before we can talk about it, of course, we have to actually choose a representation for Qi. So let's start with something simple. Let's just say that Qi is a Gaussian distribution over Z with a mean μi and a variance sigma I. So for every image in our data set, we have a different μi and sigma I that we'll keep track of. It's almost like we're trying to annotate every image in our data set with a mean and variance over its corresponding Z values. One way that we could update Qi and sigma I is just by computing the gradient of the evidenced lower bound with respect to those quantities. We'll talk about how to compute those gradients later. And then just do gradient ascent on those. But there's a pretty significant problem with this approach. This is a viable algorithm, and classic variational inference methods do use this approach. But we need a separate mean and variance for every data point in our data set. So how many parameters do we have total if we do this? Well, there's the number of parameters in theta plus the number of parameters in mu and sigma times the number of data points in our data set. This is not a big deal if you have a very small amount of data, but if you have millions of points, the number of parameters that you have in mu and sigma might be enormous. And it might make this very difficult to learn. Now remember that our intuition is that Qi of z should somehow approximate P of z given xi. So if we don't want to have this many parameters, what we can do instead is not learn a separate mu and sigma for every xi separately, but instead learn a second neural network that predicts the mu and sigma for a particular image. So we're going to actually learn a second neural network, Q, which will give us Q of z given xi. And we'll actually train that second network to be close to P of z given xi. So we'll have one network that goes from z to P theta x given z, and another network that goes from x back to Q phi z given x. And this will be the foundation of something called the variational autoencoder, which we'll talk about next.